Hi all. For section 2.2, we're starting the topic of introduction to limits. Now, while the title of the section is Intro to Limits, we've already been talking about limits. The limits that we've talked about in section 2.1 was the concept of the average rate of change, where we could say, well, all we have to do is take the average rate of change over an infinitesimally small interval. And as we do that, that's going to show us what the instantaneous rate of change is. That's really a concept of a limit there. We're making our intervals smaller and smaller and smaller. And as we do, the y value is going to approach the instantaneous rate of change, thus the concept of a limit. Now the concept of a limit, as opposed to being or having to be required to be a rate of change, we're just talking about a function's value at some point. So we'll be saying something like the limit of a function as x approaches 5. Whenever we think about that, you'd say, well, can't you just plug a 5 into the function and get it? If you can, you should and can do that. That would be the answer for the limit. If the function is defined at 5, then as it approaches 5, it's going to go to wherever it's defined. But now, what if the function is not defined at 5? Then you could say, well, okay, then the limit as x approaches 5 is simply asking me to think about what happens as x gets infinitely close to 5. And I'll have to think about as x approaches 5 on the left-hand side and on the right-hand side. So you may have to think about, well, what happens at 4.9, at 4.99, at 4.999? Those would all be values approaching 5 from the left. What about values approaching 5 from the right? You might say 5.1, 5.01, 5.001, until you can see what's happening to that function as you approach 5 from either direction. Now, if it approaches some specific y value, then you can say the limit exists. Let me go ahead and show you what I mean by looking at my computer screen here with you of my work for this section. So 2.2, Introduction to Limits. So I was already trying to discuss pretty much the concept of a limit. And this concept of a limit is not going away. You're going to be talking about limits throughout Calculus 1 and Calculus 2. So it's a fun topic. Now, the limits that we're looking at in this section are all going to be looked at using the table on your calculator or through graphs. So we're going to restrict ourselves to that right now. Later on, we'll be doing algebraic limits. And then, well, later on this chapter, we'll be doing algebraic limits. Later on in the class in chapter 4, we'll be using derivatives to find limits using a method called L'Hopital's rule. So for right now, let's go ahead and get through with a concept definition of a limit. It just says, suppose that a function f of x is defined for all x near a value of x equals a, except possibly at x equals a itself. So in other words, all I'm saying is that the function has y values for every x value, except possibly at the point where you're trying to find the limit at x equals a itself. Then the statement, the limit of f of x as x approaches a is equal to L. So what that literally means is that the values of f of x must get close to L as the values of x get close to a. So as x approaches a, the y is going to approach whatever this limiting value that we're calling L. Now, in order to show you that, let's look at some examples. If I just ask you to evaluate this function at 0, you'd say, I can't, John. Why can't you? Well, you can evaluate the numerator and denominator. The sign of 0 is 0. 0 in our denominator is 0, but 0 divided by 0 is undefined. So you'd say, okay, this function is undefined at 0. What I need you to remember, though, is that is completely irrelevant to the answer of this question. Yes, f of 0 is undefined, but what's the limit as x approaches 0? This is not necessarily asking us what f of 0 is. It's asking us what happens as I approach 0 from the left or 0 from the right. So that's what I went ahead and tried to discuss here. The first thing I was trying to think of is, well, let's think about what happens as we approach from the right. So now I've already put the y values that I got in here, but let me go ahead and show you on the calculator how this would work. Please do keep in mind that anytime you're using trig on your calculator, you need to be in radian mode. So now once I do that, I'll go ahead and say, okay, y equals, and I'll have the sine of x in the numerator, close out that sign, divided by simple x in the denominator. And now I can say, well, all right, I'll go to second table to see the graph of this. Or sorry, not the graph, but the numerical chart for this. On that chart, in order to get it like I have, please change your table setup. The independent variable needs to be on ask. So you go second window to get to the table setup. Your independent variable should be on ask. A lot of algebra classes have you put it on automatic because they want you to scroll through and see things. That is never beneficial again. So we always want to be able to input the x value and see the y value. So now I go to the table and I'll input in the x values I have here. So I start off, if I'm trying to find out what happens as x approaches 0 from the right, you don't want to start very far away. So you might just say, well, what happens at 1/10 of a unit away? So I start at 0.1. And then you say, whoa, your y value is already very close to 1.99833. Keep in mind, I had to scroll to that number to see the more exact value. If you just look at that, it's going to probably round to too few decimal places for you to be able to see what pattern is going on. Now, when I say a pattern, please try to recognize the pattern in this problem. In all of these problems with limits, there will be a pattern. So when I say, well, what if I cut that distance in 1/10 by, instead of saying 1/10 of a unit to the right, what about 1/100th of a unit to the right? When I do, I can see what's happening. Here I had 0.99833. Now I have 0.49s followed by an 833. So I can say, gorgeous, I know what's going to happen now. If I go to 0.001, 1/1000th, I'm going to have 0.69s in an 833. And notice the calculator just gives up and says, John, it's 1. Well, it's really not 1. It may be approaching a number of 1, but it never actually hits 1. So we're going to have 0.69s and then the 833. Then if I want to say, well, all right, I already know what the answer would be, but what if I go very, very, very close and only go 1/10,000th of a unit to the right of 0? I can already say it's going to be 8 9s followed by 833. Please notice that's precisely what it is. 1 2 3 4 5 6 7 8. So the pattern here, every time we got a factor of 10 closer to 0, it added 2 more 9s after the decimal, of course, making this number ever and ever and ever closer to 1. Because of that, we can say this right here. I can say this is referred to as a one-sided limit. We're approaching 0 from the right. The notation for this, I have not answered this overall question, but what I have answered is, well, as x approaches 0 on the right-hand side, because I had 0.1, 0.01, 0.0001, 0.00001. So I was approaching 0 from numbers on the right, and clearly, the closer I got to 0, the closer those y values got to 1. So I can say this little plus sign, it looks like it's up in the exponent. It literally means from the right. Now, if I approach 0 from the left, then you can say, well, all right. Now, I already knew that the y values would be the same. In fact, I did that without going to the calculator because I knew that the sine function was an odd function. X is an odd function. Odd divided by odd is even. What do you know about even functions? Even functions are always symmetric about the y-axis, so they have the exact same y values for f of x and f of negative x. You can see that here by typing in a negative point, whoops, not a negative 0.2, negative 0.1, I'll do it right eventually, negative 0.01, negative 0.001, and negative 0.0001. Please notice the y values stayed the same. You have the 0.99833, the 0.49833, the 0.69833, and the 0.89 is followed by an 833. So clearly, whether I approach 0 from the right or if I approach 0 from the left, my limiting value is going to be 1. Now, unfortunately, I will have some students that say, well, no, wait a minute, John, shouldn't I say the limiting value is 0.9999999? What number is that approaching? The number that is approaching is 1. So please don't make a mistake and try to put any one of these values as the limiting value. The limiting value is what one number all of these y values are approaching. They're clearly approaching 1. Now, in this case, since it's a left-hand limit, I would use the notation, the limit as x approaches 0 from the left of this function is 1. Now, what we've done here, and the type font doesn't show very well under the document camera for this, is we're trying to show the two-sided limit, the limit as x approaches a of f of x exists. The overall limit only exists if the two one-sided limits are equal to one another. That meaning the limit as x approaches a from the right must equal the limit as x approaches a from the left. Well, therefore, I can say, well, I just showed that the limit as x approaches a, or 0 from the right, is equal to the limit as x approaches 0 from the left. So because I've shown that, I can conclusively say, well, yeah, the limit as x approaches 0 of this function is 1. Now, if you drew a graph of this function, you know it's undefined when x is 0. I can draw an ordered pair, I can draw an open circle or a hole in the graph at the ordered pair 0, 1. I know that has to be the ordered pair because no matter how close I get to 0 on the right-hand side, the y value approaches 1. No matter how close I get to 0 on the left-hand side, the y value is going to approach 1. So it's going to approach that, and then as you move away, your sine function is going to oscillate, but that oscillation starts getting smaller and smaller and smaller because you're being divided by x that's getting larger as you go. So eventually it becomes almost a flat line on out here. Now, for our next problem, I have the limit as x approaches 16 of the square root of x minus 4 over 16 minus x. Now, what I'll need to do before I go ahead and do this problem is I need to delete out these x values. The reason for it is because this problem is going to have square roots in there, which means no negative values will be defined, so that'll cause problems. I'll go ahead and delete those out. Now I'll go back to y equals, and we'll type this question in. We still have a fraction. It's the square root of x minus 4, and then we're dividing that by 16 minus x. Get my function in, and we're trying to figure out what's happening as x approaches 16. Hopefully my choices here make sense to you, and here's the reason I chose those, because clearly if I'm trying to find the limit as x approaches 16, I can't just plug it into this problem. This function does not exist at 16. 16 minus 16 is 0. You got a 0 in the denominator, which makes this function undefined at 0. Okay, no problem. That doesn't mean that the limit doesn't exist. So I need to say, well, even though I can't just plug in a 16, I can plug in values to the right of 16. I can plug in values to the left of 16. So I need to find out what happens as I approach 16 on the right-hand side. I think it's wise to always go 1/10 of a unit to the right, then 100th of a unit to the right, and then 1,000th of a unit to the right. As we're approaching on the left, I would do 1/10 of a unit to the left, so 15.9, 100th of a unit to the left, 15.99, and then 1,000th of a unit to the left, 15.999 would be fine. Now, of course, entering these in, no big deal now, 16.1, 16.01, 16.001, we get all of those values in. Scroll over and you can see the more exact values that I had. My goal from one y value to the next is to try to see what change in the numbers there are. And so I say, well, okay, I got negative 0.1248 here. I got negative 0.12498. Gorgeous. I automatically know, okay, so what's happened here and here? It added a 9 after the 4, between the 4 and the 8. So I would look for this pattern to continue. Well, it does. Please notice. From here to here, I added yet another 9 in between that initial 4 and the 8. So if I asked, hey guys, what's the Y value at 16.0001? I am 100% confident it's going to be negative 0.12499998. And you can see I haven't done it, but I am so confident, I'll show it. 3 zeros and a 1, boom. I scroll over, negative 0.1249998. Gorgeous. Now, what this tells me is that, well, okay, this number is going to be negative 0.12499999999, as many nines as you possibly want to get to, because you can get as close to 16 as you wanted on the right-hand side. What one number is that approaching? Well, it's approaching a number of negative 0.125. So I can say the limit as x approaches 16 on the right of this function is negative 0.125, and we should recognize that as the fraction negative 1/8. Okay, now, the same idea happens on the left-hand side. I'll show that real quickly here. I can go in here to my table. I'll delete off these values because my screen resolution won't allow me to show them all. 15.9, 15.99, 15.999 should be fine. And when I do this, I can see that, well, now my value is slightly more negative than negative 0.125. When I go 1/10 of a unit to the left, I'm at negative 0.125195525. Okay, now I need to look for a pattern from this number to the next one. I can say, oh, pattern seen. It's going to add a 0 in between that 5 and that 1. Notice 195, 195 here. So I can say, okay, then I would expect this pattern to continue in this next one. It should be negative 0.125000195. Gorgeousness, oh gorgeousness. Negative 0.125000195. And then I can say, okay, then what is this going to approach? It's going to approach negative 0.125 and as many zeros as I want thereafter that. So I know that this number is approaching negative 0.125 as well. And since the right-hand limit and the left-hand limit both go to negative 1/8, we can say the overall limit also goes to negative 1/8. And I threw in a little bit of math notation there. If you hadn't seen that, the 3 dots in the shape of a triangle means therefore. So we can say, since the right-hand limit and the left-hand limit are both negative 1/8, therefore the overall limit as x approaches 16 is also negative 1/8. Now, let's show a case where that overall limit doesn't exist. Maybe. Come on. There we go. I didn't think it was going to pop up there for a second. So when I'm looking at this, I can say I have x squared minus 2x minus 15 over the absolute value of x plus 3. What I want to do is I want to look at that function as I approach negative 3 from the left and as I approach negative 3, that's from the left, and as I approach negative 3 from the right. And those type fonts really did not show up well in this video, so please note that's a minus there, that's a plus here. So from the left, from the right. So over here I thought, okay, how am I going to show what happens as x approaches negative 3 from the left? A number more negative than negative 3. So I start off with 1/10 of a unit more negative, negative 3.1. Then 100th of a unit more negative, getting closer, negative 3.01. Then I need to get closer, negative 3.001. Now you can see I put the values in there already. Let me show you how that goes into the calculator. I'll do alpha y equals to get the fraction button, and then x squared minus 2x minus 15. We are dividing that by the absolute value. The quickest and easiest way to get absolute value is just second 0, and it's the very first one, and absolute value of x plus 3. Okay, so I have my function set up. I should be able to get my answers. I'll go to my table, delete off the values from the last problem. We got negative 3.1, negative 3.01, and negative 3.001. Boom. And so now I can say, well, at negative 3.1, my y value is 8.1. Negative 3.01, it's at 8.01, and I get 8.001 for my last value. Okay, so I can see that the closer x gets to negative 3 on the left-hand side, the closer that y value is going to get to 8. I can have as many zeros after that 8 as I want by just making this value closer and closer and closer to negative 3 from the left. Therefore, what this tells me is that the limit as x approaches negative 3 from the left of this function is equal to positive 8. Now, notice my left-hand limit here. I'll go ahead and it's the exact same function, so all I need to do is just change these x values, negative 2.9, negative 2.99, and negative 2.999. This is approaching on the right. So here I'm 1/10 of a unit to the right, here I'm 100th of a unit to the right, and here I'm 1,000th of a unit to the right. The closer I get, the closer that number is getting to a negative 8. So I can say the limit as x approaches negative 3 from the right of this function is negative 8. Now, unlike the prior two examples where the limit existed because the right-hand limit and the left-hand limit were the same, it's not the case here. One side's going to 8, one side's going to negative 8. So you can say the overall limit as x approaches negative 3 does not exist. So the overall limit does not exist whenever that right-hand limit and left-hand limit do not match up. The overall two-sided limit only exists if these are the same. These both exist, but they're not the same, so the overall limit, you could either say it's undefined or does not exist, whatever you prefer there. Now, I just wanted to look at this a little bit more closely, and this will use some more of your pre-calculus knowledge, but whenever you think of that absolute value, that denominator, that x plus 3, I need you to think of every single absolute value as just a piecewise function. And the reason for that is x plus 3, it's either going to be x plus 3 or it's going to be the negative of the group x plus 3, because the only thing the absolute value can ever do is change the sign if what's inside of it is negative. So all you have to do is understand that, well, okay, when x is any number less than negative 3, like negative 4, you'd have negative 4 plus 3, that's a negative 1. The absolute value is going to make it positive 1. So the absolute value is always going to change the sign of what's inside. It's going to be the negative of x plus 3 anytime x is a number less than negative 3. But what if x is not a number less than negative 3? What if x is greater than or equal to negative 3? Well, then that x plus 3 doesn't have to change a thing because it's already going to be 0 or a positive value, so the absolute value doesn't do a thing. So I need to understand this is the denominator. It's either a negative x plus 3 or a positive x plus 3 given the different values of x. Now when I go into my function and think about it, that numerator is easily factorable. Factors of negative 15 that sum to get to negative 2. I can say, well, that's a negative 5 and a positive 3. So that x plus 3 in the numerator can cancel with that x plus 3 in the denominator. But now remember, it only completely cancels if the denominator is a number greater than 3, because then it's x plus 3 over x plus 3. But what if the denominator had to change the sign of x because the x, or change the sign of the group x plus 3 because the x was a number to the left of 3? That just means that this rational function ends up being a piecewise defined function. So I know that that x plus 3 is just going to cancel, and I would have the function equal to x minus 5 if x is strictly greater than negative 3. Now, why did I drop the equals to? Over here, I can say, yeah, the absolute value is equal to x plus 3 if x is greater than or equal to negative 3. And that's true. However, if it were equal to negative 3, this would be a 0, and you can't have a 0 in your denominator. So I just said, okay, This rational function will be defined at all values except when x is -3. When x is greater than -3, the x plus 3 is just cancel, and your function is equal to x minus 5. When x is less than -3, that denominator is going to be the negative of the group x plus 3. So you could still cancel out the x plus 3's, but then you'd have x minus 5 divided by -1, which is the same thing as a negative times the group x minus 5. You could go ahead and distribute that in and say, well, it's just going to be -1x plus 5 if you preferred. But this is our two functions. Now, when I graphed that piecewise defined function to do this overall, I already knew there had to be a hole in the graph at x equals 3 because the function is not defined there. But we've already shown up here, as we're approaching on the right-hand side, it better go to -8. As we're approaching on the left-hand side, it better go to 8. Well, that left my two open circles on the graph. You have an open circle at -3, 8, representing the left-hand limit, and you have a circle or an open circle at -3, -8, representing the right-hand limit here. So I start off with those two. Now, as I go on off towards -infinity, I just looked at this function and said, well, that's going to have a slope of -1. A slope of -1 means, okay, every time you move left 1, you'd have to move up 1. So it'd be +1 over -1. And you say, well, left 1, up 1, left 1, up 1. That means at x equals -4, the y value would have to move up 1. So I'd have the ordered pair -4, 9. Of course, you could also just plug that into your function and say, well, when x is -4, you'd have -4 minus 5, which is -9. But in this portion of the graph, it's going to change sign, and it's going to be +9. And so now for the other portion, I just said, well, it's going to be this graph for any x value after -3. I just looked at it and said, well, it has a y-intercept of -5. So I plugged in another point, and I drew them out. Typically, anytime you have lines, I will ask you to plot 2 points. In this case, are 2 open circles and one other point on those lines to define those lines. And we have our gorgeous piecewise defined graph of this function, quadratic over the absolute value. Now, so what we haven't done to this point in terms of limits is actually looking at a graph and trying to determine the limit. We've determined limits through the use of the numerical, trying to see what happens as x gets closer and closer and closer to some value of a from the left and right hand side, but we haven't physically looked at a graph of that. That's what I'm trying to do with you on this page. Now, whenever we're doing something like this, we should be able to answer the questions just by looking at what's happening on the graph. This first one here, and again, the type font is not the largest or as large as I would like it to be, but this first one is saying the limit as x approaches 1 from the left of f of x. Well, okay, all I would have to do is say, well, what happens as x approaches 1 from the left-hand side? Clearly, I'm on this part of the function down here. If x is approaching 1 from the left, the function you're on is right down here. And you can say, well, as I approach 1 from the left, at the closer and closer and closer I get to 1 on the left, the y value is going to get to -4. Do I care that there's a hole in the graph there at the ordered pair of 1, -4? Absolutely not. The limit could care less what happens at 1. It just cares about what happens as you approach 1 on the left. And as I approach 1 from the left, the limiting value is going to be 4. What about as I approach 1 on the right-hand side? Well, as I approach 1 from the right, the y value is going to go to 2. Now, again, does it matter that there's a filled-in dot there? Nope. It could have been an open circle too, and my answer still would have been 2. Well, what about the limit as x approaches 1? And here's where I want you to understand. The overall limit does not exist. Why? When will the overall limit not exist? The only time the overall limit will not exist is when the left-hand limit does not match up to the right-hand limit. Since the left-hand limit does not match the right-hand limit, the overall limit as x approaches 1 does not exist. Okay, well, what if I ask you the overall limit as x approaches 4? And you can say, well, okay, this would be 2, 3, 4. X equals 4 is right here. Now, I see an open circle at x equals 4, but what about the limit? Well, whether I approach 4 from the left or whether I approach 4 from the right, that y value is going to the exact same location. So I can say, yes, the limit does exist, unlike here where the y values do not go to the same location. Does it matter that f of 4 is undefined? No. Please remember, a limit's just caring about what happens as you near x equals 4, not what physically happens at 4. I could have defined f of 4 to be a point way down here or way up here. That doesn't affect the limit as x approaches 4 at all. Now, in this one, there's a bit of subjectivity. I just went ahead and said that that point looks like it's exactly halfway between -1 and -2. So I called that y value -1.5, and therefore the limit as x approaches 4 is -1.5. Now, f of 4 does not exist because there's no point defined for x equals 4. What about the limit as x approaches 7, and this is from the right? So you'd say, well, all right, if I'm approaching 7, right here, 7, this was 4, 5, 6, 7. As I'm approaching 7 from the right, my y value is going up to -1 here. So I can say, well, the limit as x approaches 7 from the right is -1, because as I get closer and closer and closer to 7 from the right-hand side, my y value is going to -1. What about f of 7? Well, f of 7 is 4, because it's just asking you what is the function's defined value when x is 7, and clearly that's 4. It would also be the limit as x approaches 7 from the left. What about the limit as x approaches 9? So this was 7, 8, 9. So 9 is right here. At 9, now notice this is the overall limit. So it's asking what happens as you approach 9 from both the left and right-hand side. We get the same answer again because the left-hand limit's the same thing as the right-hand limit. And you'd say, well, the overall limit at 9, and I guesstimated that that y value was -2.3 there. So I just said, well, it's approximately -2.3. And then f of 9, it's not defined where the limit is defined. F of 9 is up here at 6. Now again, hypothetically, if I ask you what's the overall limit as at x equals 7, you'd say does not exist. We already talked about the limit at x equals 1 does not exist. The only time a limit is not going to exist is when there's a discontinuity on your graph, where a big step from one side to the other. And you can say, well, okay, those are at 7 and at 1. That's going to be the only points where the limits are undefined. A hole in the graph, no problem. As long as the left and right-hand side are going to the same one, left and right-hand side are going to the same one. All right, guys, that will do it for this section. Please do try the homework for 2-2. And if you have any trouble, check with what I've done on Achieve. I had some fun working this section, and I hope you will too.